So we have discussed central force problems, some general features, right? And learn what is the spherical harmonics. So basically, if we have a potential, which in general is a function of XYZ. Suppose this is a central force problem, and then it's only a function of the distance from the center. Okay, so this is the central force problem, right? Okay, and then in this case, the Schrödinger equation has a rotation symmetry, right? So then we can use the spherical coordinates to write down this wave function. Okay, and this one, we know that in the spherical coordinates can be written as minus h bar square over 2m, and then what's inside is the Laplacian. Okay. Right. Sin theta, sir. Okay, so this is the kinetic energy, right? And then you have potential. Okay, so this one has a rotational symmetry. Okay, because of this rotational symmetry, so we have Hamiltonian and the total angular momentum squared equal to 0, and then Hamiltonian and one of the components, and all of the components actually of the angular momentum equal to 0, and of course we also have L square and LC commute, right? So because of these three operators commute, so they can have a simultaneous eigenstate. Okay, right. So that can be written as a function with 3 index. Okay. So that can be written as a radial part of the function, which is a function of R, and of course has 2 indices, N and L, and then have a spherical harmonics. Right, and this M is called a principal. Quantum number. And L is the angular quantum number. Okay. And M is the magnetic. Okay. Right. And this YLM can be written as associated Legendre functions, okay, and times e to I m's. All right, that's called a spherical harmonics. Okay. right? And the energy is the same for different m. Okay, and we know that this L equals to 0, 1, 2, 3. They are integer numbers. Okay, and m equals to 0 plus minus 1 and up to plus minus L. So they altogether the 2L plus 1 degeneracy, right? Of energy. Okay. Right. And this is spherical harmonicas. Okay. So they are eigenstates of the angular momentum squared with the eigenvalue L times L plus 1 h bar squared Lm. And of course, it's also the z components eigenvalue with eigenstate with eigenvalue m times h bar. Okay, right. So this has been what we have learned last time. Okay, right. So this is the case for general central force. Problems. Okay. So today we'll try to apply this theory to a very important problem. That's a hydrogen atom problem. Okay. Okay. Okay, so I will switch the whiteboard because there's some problem with the original one. Okay, so you can see the white screen, right? So the whiteboard, right? Okay. So now today we're going to consider this hydrogen atom problem. Okay. And in this case, of course, so suppose we have the Coulomb interaction, right? So we have a Coulomb potential between two charges, say Q1 and Q2, right? For example. Okay, and then the potential, of course, is just Q1, Q2, 4 pi epsilon 0, and R, say 1, 2. Okay, so R1, 2 is the distance, right? Okay. So this one actually can be reduced to the central force problem. So if we have a proton and the electron, okay, so we have Q1 equals to E and Q2 equals to minus E, and then this VR just equals to minus E squared 4 pi epsilon squared and R, and this is just proportional to 1 over minus R, right? So that's a very special central force problem. Okay. Okay. And this problem actually has a lot of applications, right? So you can have the hydrogen atom. This is basically the proton and the electron. You can also have you know, for example, you can have deuterium. So you have a proton and a neutron and the electron, right? So the mass is different. Okay, you can have a helium, but ionized. Okay, so it's a positive charge. In this case, you have the alpha particle and the electron. So Q1 equals to 2 times E, and the Q2 equals to minus E, right? So in this case, we say VR equals to minus J E squared for 4 pi epsilon 0 R, and with C equals to 2, okay? Right, so this is the case. And also you can consider, for example, lithium, but now you have 2 electrons removed. It's ionized, right? So you have, and again, it's not an alpha particle anymore, but you have Z equals to 3, right? You can also consider a case, for example, you can have the positron and the electron, okay? So this is the positron electron. You know that they also have this Coulomb force, and the charges are the same as we have for hydrogen atom, but the mass, of course, is different, right? So you can also have the proton and the mu particles, okay? And in this case, you still have Q1 equals to plus E, and the Q2 equals to minus E, and then the mass of the electron is just heavier, right? You can also have electron hole pairs in semiconductor, for example. Okay, a lot of optical properties actually of semiconductors are related to the this kind of hydrogen atom, but of course it's effective hydrogen atom problem in semiconductors. And sometimes there's also shallow defects, such as donors in semiconductors. So in this case, sorry, it looks like the internet was disconnected. So where did we pause? Did we lose the connection? Can you let me know which part did we? Okay, semiconductors. Okay, that's okay. So I think it's just a little bit lost. So it's okay. Okay. So we consider proton and electron. So let's look at the Hamiltonian, the classic Hamiltonian. Of course, you have the kinetic energy of the proton, and you also have a kinetic energy of the electron, right? And then you have the interaction between them.
Professor, I think
Yes.
you are not sharing your screen.
Oh, sorry. Okay, now you can see that, right? Okay, great. So this is the Hamiltonian between the electron and the proton. Okay. And if we change this one to be quantum mechanics, what we need to do is to make this one to be operators. Okay. But now this is a 6-dimensional problem, right? It's of course is very difficult, right? So you have you know, XE, YE, ZE, and XP, YP, and ZP, right? So you have 6 coordinates. Okay, so the operator is acting on this 6-dimensional space, and then you have a wave function. But in classical mechanics, we already know that there is the separation of variables that we can do, right? Again, because of symmetry. So we can have the center of mass and relative motion, right? Okay. So then we can say that we can define the momentum, center of mass momentum, that written as the electron. Sorry. Right. And the relative 1 equals to this one, right? Okay. I think probably there's a typo in the lecture notes. Yes. In defining the momentum, I think there is a relative. There's a typo in this definition. Okay. So if you check the lecture notes in page 160. Okay. So this should be the center of mass and the relative motion. Okay. And the mass, total mass, of course, is just ME plus MP. And the reduced mass, we can say this is ME times MP and divided by ME plus MP, right? So that's the, and then we can write down this Hamiltonian. Okay. So the Hamiltonian now can be written as 2 parts. One is the center of mass part. Okay. Okay, and then you have another one. So that's the relative motion part. And this one is given by the motion of the reduced mass. Okay. And then plus, sorry, minus E squared over 4 pi epsilon 0 and R. Right. So this part is the one that we are interested. Okay. So this way, so we can either just ignore this center of mass motion, right? So we are just consider the relative motion, only the relative motion. Okay. So this Hamiltonian can be, I just you know, by the abuse of symbols, I just call this Hamiltonian. Okay, but actually I have dropped the center of mass motion, and this is p squared over 2m minus 4 pi, sorry, minus E squared over 4 pi epsilon 0 and R, right? is a standard central force problem. Okay. Right. Right, and of course this m actually should be mu. Of course, if you take the mass of the proton much greater than the electron, take this effect into account. So this will becomes roughly just the mass of the electron, right? Okay. And sometimes we can also say that we can say that taking the proton to be infinitely heavier, okay. Okay. So that it has no motion. Okay. So in some sense, we say that you can simply just say that we can take this one to be 0 by make this one goes to infinite. Right. So that means we just neglect the motion of the proton and consider electron motion, to be the only interesting part. But actually, the real meaning is that we are considering the relative motion. Okay. And the center of mass, you can see that it's just a free particle. Okay, the center of mass is just a free particle. So its solution is just plane waves, right? So it's that's very simple. Okay, so this is the Hamiltonian, right? And then we can just consider the eigenstate again. Right, so and this Hamiltonian can be changed into this one, right? So that's the Laplacian times minus h bar squared over 2 mu minus e squared over 4 pi epsilon r and per psi r equals to e per psi r. Sorry. Right. Okay. And then we know that this per psi can be written as r m l r and y l m theta and phi. Right. And this energy can be written as E m l. That's already we know that from the central force problem, right? But actually, we can know more, okay, because of this special 1/4 potential of the hydrogen atom, okay. Okay, so that is the general formulation of this hydrogen atom problem. Right. So let me recap this Hamiltonian. Okay. Right. And we know that in the harmonic oscillator, so we have length scale, right? Remember LC, energy scale, h bar omega, right? And a momentum scale, of course, right? So that one can be just given by the length scale and the energy scale, okay? How about here? So in the hydrogen atom, we can also define the typical length scale and the energy scale. Okay. Of course, you can also say that you have a momentum scale. Right. So this is unique for quantum mechanics because of we have h bar. If we don't have h bar in the classical Coulomb force problems. Actually, we don't have any typical length scale, energy scale, momentum scale. So that means the system, do not assume any special energy or special position, special distance, whatever. But in quantum mechanics, because we have H bar, we have this epsilon 0 and E square and M, okay, so that we can actually obtain the kind of energy, okay. To do this, okay, now you can say that, like for example, you can have H bar square over 2M. Remember, this one has a dimension. It's the length to -1, right? So that means if we times, a length scale square right here, this will be dimensionless, right? So what we need to do is just to put an A, B right here, okay? Right. So this is one thing. So first of all, we can have, the energy. Okay, we call this one energy scale. This one length scale. That will equals to H squared over 2M and AB squared, right? So that's one thing, okay? But you have two variables, so you cannot determine this one, right? And then you can also look at this. Okay. And this one has length scale, right? So if we put AB right here, you put AB right here, okay? So this one will be the energy, right? Okay, so that means we can also write down this as EB equals to E squared over 4 pi epsilon 0 AB. Okay, so now you have two equations, right? Sorry, this is not EB. We actually call this one R. For some reason that will be clear later, we actually divide by 2 right here, okay? So that this one equals to 2 times RB times AB over R. So this is dimensionless, okay? Right? So the reason actually will be clear a little bit later, okay? And of course, this momentum is just H bar times AB to -1, okay? And from this, so you can immediately obtain this so-called Bohr radius as the length scale. That is AB equals to 4 pi epsilon 0 H bar squared over ME E squared. This is roughly just 0.0529 nanometer, or equals to 0.529 angstrom. Okay. And the energy scale equals to H bar squared, as we said before, is AB to -2, okay, over 2ME. I think there's also a typo in the lecture notes. It should be AB to -2, okay, not to power 2. And this one equals to half of E squared over 4 pi epsilon 0 AB equals to ME E to the power 4 and 32 pi squared and epsilon 0 squared and H bar squared. Roughly it's about 13.6 electrons. Okay, so these are it's called the Rydberg energy. Okay, it's related to the Rydberg constant. Okay, so related to the, we know that this one is equals to just H times nu. That's HC over the lambda and typical length, right? And actually, it's called HC over R. Okay, H. So this one is related to the Rydberg constant. Okay. which has the dimension of length. Okay, but anyway, so that is the typical length scale and energy scale for hydrogen atom. Okay. And now, if we write down this one, and in this length scale, so the Hamiltonian just becomes R, the Rydberg energy times, minus square plus 2 over R level 2. Okay. Okay, important. And here and R are dimensionless. Okay, so that means once you obtain the wave function for this operator, you basically just change all the lengths to be the length divided by the length scale. Okay, and then you obtain the wave function in the original units. Okay. Right. Now you can see that in the case if the momentum equal to 1 and the length equal to 1, and you got the energy equal to -1, right? Or minus energy. So that is why we take the factor 1/2 over there. Okay. So this is also related to the so-called virial theorem. Okay. So next we know that kinetic energy times 2 always equals to minus m. Sorry. Yeah, minus m times the potential energy for V is 1/m. Okay. So this is actually the special case of the virial theorem. Okay. So you have the virial theorem, and the kinetic energy and the potential energy has a relation. Okay. In our case, so we have 1/r potential. So the kinetic energy is always half the negative potential energy, right? So that's why. So once if we put in the cluster system, you put the electron at the distance RB away from the center from the proton. So the kinetic energy and the potential energy will be just 1 Rydberg energy and -2 Rydberg energy respectively. Okay. Right. So that is the energy scale. So this is so you can see that this energy scale defines everything that we are going to discuss later, right? So once we say anything about the quantities, so you always keep in mind what is the length scale, what is the energy scale. This is basically the size of the atomic sense. So if we talk the size of the atom, it's roughly a few times or just similar to AB. If we talk about energy, it's just about the electrons, right? 10 electrons or few electrons. So in this sense, we say that so this electrons, okay, means the energy charge times watt. Okay, it's about 1.602 times 10 to -19 joule. Okay, so that's the energy of electrons, and this energy actually is a very important energy scale. Okay, so it's basically it's about the energy. It's the energy of an electron at a potential V equals to 1 watt. Right. So this is important. This is actually it's kind of it's a human energy scale. For example, if you look at around of the environment around you, so everything seems like at this energy scale. For example, visible light. You have H nu is about 1.5 to about 3 electrons. Okay. If you look at semiconductors, the band gap is about a few electrons. So actually, for all the solids. Okay, so you look at the temperature, the melting temperature, Kb T melting will be just 1 to 10 electrodes. So all the solids around you, okay? So there is actually a reason, okay? That's because all of this and all of the chemistry, biology, and these solids that around us are because of the chemical reactions, okay, between atoms. So that involves the change of the states of electrons in the atoms. And this energy scale, of course, is given by roughly, this Rydberg energy. So that's why electrodes is so useful energy scale for us. It's so biological, so human, right? Because we are made of molecules. All of life process actually are based on the chemical reactions, which involves the transfer of electrons from one molecule to another molecule, from one atom to another atom, which involves the energy change in the order of Rydberg energy. That's 13.6 electrodes. So a few electrodes actually is a very important energy scale for biological process, for human beings, for the environments, daily life environments around us, okay, including the light, including the chemistry, including the solids, semiconductors, all these things, okay? Right, that's so much about this energy scale, okay? Right, which is always important in physics. The scales are important, okay? Right, so if you want to study physics, you should keep in mind the energy scales, okay? All right, another eigenstate, of course. Right, so the eigenstate, so we should have Hamiltonian, acting on this eigenstate equals to E ml mlm, right? And this wave function, if you of course, right? Okay. And then the question is, right? So that is what we wish to obtain, okay? So let me first of all write a few effects on this one, and then I will just go briefly the mathematical processes for obtain these results, okay? But I leave it to you for you to read more on the appendix in the next notes, so that you can know more details about the solutions, okay? So the energy, so the important thing for this 1 minus 1 over R potential, okay? Okay, we have all of this E m now actually equals to EM. So it's independent of L. So that's one thing very important. Okay, that's secondly, for M equal to 1, 2, 3, and so on and so forth, L actually can equal to 0, 1, 2, and up to M minus 1. Okay, so L is always less than M. So this is another important feature, okay, for this solutions of this one. Okay, so that means, for example, if M equal to 0, N equal to 1, so you have L equal to 0, and then M must equal to 0, right? Okay, so that's the only possibility. So the degeneracy D equals to 1. So all of these states have the same energy, okay? Or M equals to 2, and you can have L equal to 0, M equal to 0. Or you can have L equal to 1, and M equal to 0, or plus minus 1, right? Okay. Usually, and this one, they have different energies. But now, because of this 1 over R potential, so because of 1 over R potential, okay, they have the same energy. Okay, so that means this D equals to 1 plus 3 equals to 4. Okay. You can also consider the case that m equal to 3, for example, and you can L equal to 0 and m equal to 0, or L equal to 1 and m equal to 0, or plus minus 1, or L equal to 2 and the m equal to 0, plus minus 1, plus minus 2, right? So all of this one have the same energy, and then you have D equal to 1 plus 3 plus 5, and that equals to 9. And so obviously, so you can see that so the degeneracy okay. So the degeneracy, you find that this one equals to EM. So degeneracy D equals to M squared for M equal to 1, 2, 3, and so on and so forth. So that's the results for the energy. Okay, now how about the wave function? And this wave function actually can be written as r to the power L, 1 plus a polynomial, and a1r plus a2r squared, and so on and so forth until you have a m minus l minus 1 r to the power m minus l minus 1, and then times e to minus r over m. Okay, and this r is dimensionless. Okay. Okay. And the reason of this one is that it's because of the physical boundary conditions. Okay. Right. So that's the main result. Okay. We will discuss the features of this energy and states more, and also discuss a little bit how to derive this, how to prove this kind of results. Okay. But let's take a break at this point. Okay, and then we're going to discuss more details on the results. Okay. All right, so let's look at this radial part of the wave function, right? So we know that we have minus r squared minus 2 over r. That's the dimensionless Hamiltonian, right? On this wave function, that's r theta phi equals to the energy psi r theta phi. Okay. Of course, we have this r theta phi can be written as the radial part, and then times the spherical harmonics. Right. So that's what we have known. Okay. And then this one immediately obtain the the Schrödinger equation for this radial part. Okay, so that is minus r squared and d over dr and r squared and d over dr. Right. So this is the radial part, and then we have the angular momentum part, right? So L times L plus 1. That's the angular momentum squared, okay? And divided by R squared. And then you have this R over 2, 1 over R potential, okay? It's minus 2 over R, okay? So this should equals to energy R, okay? And then we can solve this problem by the series solution, okay? But to do that, actually we want to separate some essential parts and some some easy parts. Okay, so we had some experience with the harmonic oscillators, right? So here we also do some guess. Okay, so the guess is that this function should be something like e to kappa times r divided by r, and then times another function 1r. So the question is why, right? So why this form? Okay. So there are actually two reasons. Okay. There are two considerations. First of all, and for the free particles, in the spherical coordinates, you know the solution is that you know e to I k r over r. So it's called a spherical waves. You know that the meaning of this one, right? So you can see that this one easily you can see that this r squared just is 1 over r squared, right? So the probability goes like 1 over r squared. So it's like a flux that goes as with density as 1 over r squared, and then the conservation of the flux, right? Make sure this this wave function is assured by this wave function, right? So this is spherical wave. So we guess this one. So this is for the energy equals to h bar squared k squared over 2m. That's positive, right? But now for the bounded state, we have energy to be negative. So we guess that this energy. So we guess that maybe if the energy is h bar squared k kappa squared over 2m, right? So that gives us e to minus kappa r over r, something like this one, right? This one is of course for the free particles, but we have 1 over r potential, so we have this correction, right? Okay. So if there's no interaction, there's no potential. Okay. So we guess that the electric energy would have this kind of exponential decay, right? So that's one thing. And another thing that you may wonder, 1 over r goes to infinite at I equals 0. So how do we deal with this the divergence, right? So actually this is okay because the probability, for finding the electron in this one is given by PHYS squared times r squared dr, remember, right? Because if we do the three-dimensional integration, it's r squared dr sin theta d theta and d phi, right? So that's because with this r squared, okay, so we are allowed to have this 1 over r. Okay, so that's why we can have a function like this one. Okay, so in general, you can have 1 over r. But of course, later on we see that this 1 over r actually doesn't really exist because for the 1 over r potential, so the wave function actually will decays to, will behaves quite smoothly at r equal to 0. Okay, not that smoothly, but it will not diverge at r equal to 0. But in general, the wave function for the center force problem can have this 1 over r divergence, okay, without violating any physical requirements. Okay, so that is a special case. Okay, so with this one, you put this one into that one, so you got an equation for y. That's a lot simpler. Okay, so you got a minus d over dr squared plus 2 kappa d over dr and plus L times L plus 1 over r squared and minus 2 over r. And this y as function y, this will equal to 0. Okay. So we find the energy will just equal to minus kappa squared. Okay. Right. So by inserting this one into the Schrödinger equation, we got this equation. Okay. And then you write down this y just equals to A0 plus A1 R plus A2 R squared, and so on and so forth. Okay, you put this into that one, you obtain immediately AJ plus 1 equals to 2 kappa J minus 2 and J times J plus 1 minus L times L plus 1 and times AJ. Okay, so this is the iteration equation that we're going to obtain by just using the series solution of this one. Okay. Right. So with this one, so you can see that immediately you wish this one to be terminating, right? Okay. So you can see that if it's not terminating, okay. So if so from that one, you can immediately obtain that this AJ will be roughly just J factor times kappa to the power J, right? Okay. So that means you eventually got this Y is going to in the order of e to 2 to the power J. 2 kappa J, all right, 2 kappa R, sorry. And then that equals to, that leads to this R is in the order of e to kappa J, so kappa R, sorry. And that goes to infinite, and R goes to infinite, right? It's unphysical. So this means we must have a terminating series, okay? So the only possibility that this kappa times J equals to 1 at certain J, right? Okay. So that means this kappa can only equals to 1 over J. Okay. That equals to, for example, 1 over 2, 1 over 3, and so forth. Okay. And then this energy. So this immediately obtain that the energy must equal to minus Rydberg over 1 squared minus Rydberg energy over 2 squared, and so on and so forth. It's minus Rydberg squared over n squared, right? Right? It's independent of L. Okay, so that is important results. Just to require the wave function to be physical, we find that this energy has to be quantized. Okay, so we call this one EM. Okay, so that's one thing we obtain immediately. Okay, and secondly, you can see that. So let me write down this one again, right? So AJ plus 1 equals to J times J plus 1 minus L times L plus 1 and 2 kappa J minus 2, right? So this got one result is that the energy E must equal to minus Rydberg over 1 squared or minus Rydberg squared over 2 squared. And so on and so forth is minus Rydberg, sorry. Let me just say that the energy must take some discrete values. M equal to 1, 2, 3, and so forth, so on and so forth, right? Or kappa equals to 1 over 2, 1 over 3, and so on and so forth. Okay, so that this wave function is this polynomial is terminating, and so that we have the function is not the divergent at infinite distance. Secondly, so you can see that if you look at this term, this one should not equal to 0, right? Otherwise, you're going to have a divergence. Okay, so that means and this J should take some values that should be a certain large enough. Okay, so all the terms below a certain term should be 0. Okay, so that means AJ should equal to 0 for J less than or equal to L, right? Otherwise, you're gonna have a certain term will be infinite, right? Otherwise, you must have a L plus 1 equals to infinite, which of course is also unphysical, right? So this means that this kappa, or this 1 over kappa should take values to be at least L plus 1. So that means this M should equal to L plus 1, L plus 2, and so on and so forth, right? For each L, okay? For each angular quantum number. Okay. But of course, we can say that if I fix M, okay, or if M is fixed, that means the energy is fixed. Okay, so L will just equal to 0, 1, and so on and so forth until M minus 1, right? Okay, so this is why that we have this limitation on this angular momentum. Okay, so the physical condition give us two results. One is that this energy is going to be quantized and degenerate for different L. Okay, and secondly, and this L will be limited by M. Okay, they cannot be arbitrary numbers. Okay, and the wave function. The third point, this wave function, okay, now can be written as AL plus 1 plus AL plus 2 times R until you have AM, right? R to the M minus L minus 1, okay? And then times R to the power L times e to minus R over L. Over M, sorry. Okay. So the wave function is also obtained, and the coefficient is given by, by this iteration equation, right? It's given by this one. Okay. So once you fix one coefficient, say for example, you need AL plus 1 equals to 1, and then all the other terms will be obtained, right? So this gives us the energy and the quantum numbers and all of these wave functions, okay? So the wave functions actually are summarized, a few examples are given in the table, in the lecture notes, okay? So I will not repeat that one. So we will come back to a few examples later, okay? But let me just summarize what we have, okay? Right, so first of all, for each M, this M can be 0, can be 1, 2, 3, any positive integer numbers, and the energy EM just equals to minus the Rydberg energy over M squared. Okay, right? So that's the energy, and so the important thing is that it's independent So the energy. So energy is independent of L. This is special of minus 1 of R potential. Okay, it's not true for general potential. Okay. Now, secondly, for each m, L equals to 0, 1, 2, until m minus 1. We already know that for each L, m equals to 0, plus minus 1, plus minus 2, and so on and so forth, and plus minus L, right? So they altogether there are 2L plus 1 choices. Okay, they altogether you have n choices, right? Okay, so if you call this data, for example, if n equal to 0, so this is 0, 0, 0, right? Sorry, 1, 0, 0, 0, n equal to 1. So this is n equal to 1, L equal to 0, and m equal to 0, right? So this is only one state. And this state is called 1s states. The energy, of course, is minus 13.6 electrons. That's minus divided by 1 squared, right? And then you have the other states. So you have, for example, and this one is, so it's 2, 0, 0. Then we call this one 2s. And you have 3 states. That's 2, 1, minus 1, 2, 1, 0, 2, 1, plus 1. And these are called 2p states. So altogether, you have 4 states, right? And then, so the energy of this one, of course, is minus readable energy divided by 2 squared. So that's 1/4 of this readable energy, the negative, right? Okay, and then you have another one that's 2s, 3s, 3p. And you have also 1, 2, 3, 4, 5 states. That's 3d, okay? And you can even have like a 4s, 4p, that's 3 states, and 4d, there are 5 states. And 4f, there are 7 states. They all have the same energy. That's a readable energy divided by 4 squared, right? Until, of course, you can have they get closer and closer to 0, right? So above this one is the so-called continuum states. That's energy to be positive. That's called scattering states. We are not going to study right here. Okay. So the degeneracy, you can look at the degeneracy equals to 1 plus 3, and so on and so forth, until you have 2m plus 1, right? Minus 1, sorry. So that equals to m squared. Okay. So this is the degeneracy, right? And the states as I showed right here. Okay. So we call the states, the labeling is 1s, 2s, 2p. There are 3 states. 3s, 3p. There are 3 states. This is for the L equal to 1. And 3d. This is for L equals to 3. So the 2, there are 5 states. And 4s, 4p, 3 states. 4d, 5 states. 4f, 7 states. If you want, you can go continue this one. You can for 5s, 5p, 5d, 5f, 5g, and then 6, so on and so forth, right? So you can have different labelings. And now you can also consider the emission, right? So if you look at the emission, so you know that this one can goes to this, okay, right? Okay, so these are the emissions or the absorptions, from the states to other states, and this one is called the Lyman series. Of course, the energy or the wavelengths can be, so you can have HCl lambda. So this will equals to and the readable energy, 1 squared minus 1 over n squared, right? So that is this Lemons series. Okay, so that's the emission. This is actually the ultraviolet. It's a UV. Okay. But of course, you can also have emissions, say, to the 2s or 2p or 2d states. Sorry, 2p states. So you can have something like this one. Right? Okay. So you can have, for example, okay, all of this one. So these states are called, this is just the one that was first discovered, called the Balmer's series. The Balmer series, okay. So this, of course, is visible. So that's the one why it was first observed, okay. Right. So the energy is also determined by this readable energy, times 1 over 2 squared. Okay. So this one is 1 over 2 squared minus 1 over m squared, times the readable energy, right? Okay. So that's the Balmer series. And you can also have other series, okay. For example, you can have the emission between the third shell and other states, right? So you can go like this one. Okay. Right. So you can have all of others. Okay. So this one is called the Parsons series. Okay. So the energy is 1 over 3 squared minus 1 over n squared times the readable energy, right? Okay. The photon energy. And this one is infrared. Okay. So there are many. Okay. Actually these days, people can set the hydrogen atom to very, very high quantum numbers. So they can have even series in the microwave, radio frequency waves. Okay. So they can have a very small energy scales, to be observed. Right. So this is the feature of this this energy states, okay, and also the wave function, as we said before, this wave function. Let's look at this wave function again, okay. Right. So this one can be written as say r to the power L, okay, and then the first one can be written as 1, for example, and then you have a1 times r plus a2 times r squared, and so on and so forth, and then the highest order term will be am minus l minus 1 times r m minus l minus 1, okay, e to minus r over m, okay. So this is the general feature, okay. Right. First of all, you can see that if L does not equal to 0, then you have RML R equal to 0 at R equal to 0, right? Actually, it's R to the power L, right? 0, right? So this is actually required by physics, right? Because you can see that, remember the wave function is given by RML Y LM theta and phi, right? This is function of R. So you can see if L is not 0, and this YLM is not a constant, right? So that means if this radial part is not 0, so this one equal to 0 at R equal to 0 actually guarantee the single value set. The wave function is a single valued, right? Okay. So if this one is not, and it should happen this one to be a single valued, okay? So this one is similar to the vortex. Now you know that if you have some, say, if you have some vortex, Okay, that means the water, for example, is just a flow. Okay, and you have a velocity theta and phi, which is not 0. Is right around this vortex. So that means the density this must be 0 at I equal to 0, right? Otherwise, you cannot have a well-defined a velocity field for the vortex. Okay, and similarly, so if we have a wave function of L to be non-zero, and then this angular part is harmonic spherical harmonicus, so they are not constants. And then to guarantee that the wave function is single value, so at I equal to 0, remember there the theta and phi are not well defined, right? So they can be any value, right? So then that means the wave function could be any value. This is not physical. So the way to make this one to be correct, so you must have for this radial part to go to 0. Okay, so this way you have this one to be well defined, this wave function. And actually you can see that if you have larger L, that means the spherical harmonic is more oscillating, around the angles. And this radial part must be more 0. So it's higher order 0. Okay, so that this wave function is better behaved. Okay, right. So that's one thing you need to pay attention to, right? And secondly, so if you look at this part, okay, so this part 1 plus A1R plus so on and so forth plus AM minus L minus 1 to the power M minus L minus 1 actually has exactly M minus L minus 1 roots. Okay, so this is also future. Okay, so that means if you have, for example, if you have say n equal to 3, L equal to 1, okay, and then this one will become just 1 plus A, the highest order will be A1, right, times R, and then times R, sorry, let me see, M minus, yes, this is the 3p states, right? Okay, and then times e to minus r over 3, and this one has 1 0. Okay, so this one has 1 0 at 0. Okay, so altogether, so if you take the 0, I equal to 0 as the lth order 0, so altogether you have m minus l minus 1 plus l roots. Okay, if r equal to 0 taken as L roots, because the wave function equals to 0 and L times at the I equal to 0, right? So you can take the I equal to 0 as the Lth order roots. So altogether you can have m minus 1 roots. Okay, right? So that is another thing that we can notice. Okay, and then you may wonder, it looks like how many roots actually determined by this L and M, right? So if you have a larger L and the number of roots, so this one goes down if L goes up, right? So this is different from what we have in the one-dimensional problem. In one dimension, we know that if you know the energy, the Lth order, the Lth energy level would have L roots, right? But here it seems that the roots, the number of roots is not totally determined by this energy, okay? But also determined by this angular momentum L, okay? So Y, okay? So we're going to later. So when we discuss more on the features of this different angular momentum states, we're going to say that actually, so if you count the number of nodal surfaces, okay, you will see that there's something interesting. Okay, so but let me keep that one for a while. Okay. All right. So another thing that I think one of you asked the question about the fading, the of electrons, right? Fading the shells. Okay. So if you have multiple electron, have multi-electron atoms. For example, lithium. Okay. And they have different levels, right? So you will need to have 1s, and they have 2s, and they have 2p states. Okay. Of course, you can have some other states. So the energy is another scale. Okay. 3s, 3p, 3d. Okay. Right. And how would the electrons to be filled if you put more and more electrons? So let me take the zeroth order approximation, okay? And this kind of interaction neglected, okay? And also we know that the electrons are called so-called fermion, okay? And they have to satisfy this Pauli exclusion principle. That means you cannot have two electrons in the same state. And also there's one thing we haven't talked about, the spin. Okay, so each orbit has two spin states, say up and down. Okay, so that means if you put electrons right here, you first of all you put one electron in this lowest energy state to make this atom to be at the lowest energy state, and then the next one will three are here. Okay, but now you have to put this electron to be in the spin down state. Okay, right. So this one is for example, helium. And if I have one more electron, and then you will put it right here. Okay, so this one is for the lithium. Okay, right. And for some reason it will not be in the 2p states, right? So that we are not to discuss right here. Okay, because of some interactions. Okay, so that this lithium prefer to stay in this and then the next one you're going to have this one to be occupied. Okay, so you can have four electrons. They're both in 2s states, and 1s or 2s states. Okay, s orbits. And then you can say that if we have more electrons, what will happen? So you can actually say, for example, you can put right here, and now all the electrons are in the spin up states. Okay, okay. So you can just keep putting this way. So the electron will fill the shares one by one, and starting from the s and then p and the d orbitals. And but of course, if the quantum number goes very high, if the principal quantum number is big, and then the interactions will make all of these things to be more complicated. But roughly, this one will be the case. Okay, so that one explains the chemical properties, okay, especially the periodic table. Right, so you can say that after the second shell to be filled, for example, if this has been filled, okay, so then you need to put another one right here, right? But this one is just the sodium, right? So the lithium and the sodium will have the very similar, chemical property, okay, because they have the same electron in the s states, okay. One is in the 2s, another in the 3s, right? So that is why we have periodic tables, which actually tell us, those atoms with a certain number of electrons would have similar chemical properties. Okay, and you can see that we can already got some clue from the states of the hydrogen atom if we make sure this electrons, fill the shells following this kind of rules, right? Okay, but this is very rough, so I have to emphasize this is a zeros order approximation. Okay, you need to go to high orders, so take into account the interactions and take into account the spin of the couplings, taking into account the screening and so on and so forth. Okay, to understand the more complicated, more realistic structures of these shells in atoms. Okay, especially in these multiple electron atoms. Right, so that is another thing. Okay, and one more thing. Okay, and so we have the Virial theorem. So we are not going to prove right here. So in classical mechanics, we know that we have the kinetic energy times 2 equals to actually is partial V partial Ri times Ri, and this one. Okay, and so this one is going to be simply just minus m and V. So if V is the order of is proportional to 1 over r to m, right? Okay, so this one can be generalized to quantum mechanics. So there's minus sign, sorry. Sorry, the minus sign m goes to V, right? So in our case, sorry, I think it's correct because this is 1 over minus 1 over r to the power m, right? Okay, for all cases m equal to 1, so you basically have 2 kinetic energy equals to minus the potential energy. Okay, right? So in particular, if we have this em equal to minus readable energy divided by n squared, so you can say that the kinetic energy actually will equals to the readable energy divided by m. Okay, and the potential energy will just be twice of this one. Okay, you can check this one, for some states. Okay, so check. So eigenstates. Okay, that's exercise. Okay. Right. In particular, if you have the quantum state, so the electron will have the kinetic energy to be about just the readable energy, and the potential energy will be minus 2 times the readable energy. Okay. Right. And then there's another misconception of so this RMLR modulus squared is not the probability and density of it's not a probability of finding this particle in R and R plus dr. Okay. Okay. It's not. Okay. The reason is that the total probability is that remember is percent modulus squared times r squared dr sine theta d theta d phi. Sorry, and this one can be written as modulus squared r squared dr and d omega. D omega is just an integration over the solid angle. Okay, it's 2-dimensional space. So that means you need to take into account the measure, of R. The reason actually is very simple, right? So remember, if you take the sphere, and this one is this is R. This is R plus dr, right? And this volume actually is the volume equals to 4 pi times r squared dr, right? Okay, so that means we need to take into account this measure to quantify the probability of finding the particle at a certain position, right? So the probability in R and R plus dr is given by PR dr that equals to RMLR modulus squared. And this one is a real function, of course, and then R squared dr. So we actually have this one to be PR. Okay, so that is one small thing we need to make sure. Okay, for example, if we want to calculate the average distance of this electron from the nucleus, so this will equal to PR times R and times dr, right? So that equals to actually R cubic RML and dr. Okay, so this is just a small detail you need to pay attention to this. And in the homework problem, we're going to work one problem on this. Okay, so that you can pay a little bit more attention. Okay, but it's not really very difficult to understand. Okay, it's just very simple stuff. All right, I think this is pretty much the overall properties of this state. And next time we're going to have a talk, okay, to show more examples of those 1s states, 2s states, 2p states, 2d, 3s, 3p, 3d states, and so on and so forth, so that we get more familiar with those states, okay? Because it's interesting to know those the shapes of those orbitals and to have more knowledge about those spherical harmonicas, okay? And we're going to have some pictures next time, but for the moment, I think we have pretty much some basic knowledge about those eigenstates and of hydrogen atom. Okay. Right. Okay. So we're going to stop right here. So in case you have questions, so please just put in the chatting room or just raise your hand.